Alright, so how to play a basic game and what is some basic terminology that we need. So let's begin with players, strategies and playoffs. So obviously to play a game we need to know who the players are. So players could be individuals, could be firms, could be countries. And then the players need to have some strategies. So if they are firms, they may either increase the price or lower the price. And if they are countries, they may liberalize or become more protectionist or pursue peace or go to war. And we need to know the payoffs associated with different strategy combinations. And again, game theory is about non-cooperative situations. We don't know what the other player is doing. So those are non-cooperative strategic interactions that we are dealing with. So let's take a look at a game, and what you see is a game in so-called normal game, in normal form. So you can see we have two players, player 1 and player 2. We know their strategies. Player 1 can play up or down and player 2 can play left or right. And we see the payoffs depending on different outcomes of strategies pursued. So if player 1 plays down while player 2 plays right, player 1 would get 1 and player 2 would get 0. So how do we play a game? When playing a game, you need to essentially ask 4 questions. And in doing so, you put yourselves in the shoes of each player. So let's start with player 1. Player 1 needs to ask themselves, what is my best strategy if I think player 2 might play left? Shall I play up or down? And in this case, down is better than up because down has a payoff of 3 as opposed to a payoff of only 1 for up. So that's why we underscore the 3. But player 1 also needs to ask themselves, what is my best strategy if player 2 plays right? Shall I play up, get 0, or shall I play down and get 1? And of course the best strategy is then again to play down because 1 is bigger than 0. So now player 1 plays down. No matter what the player thinks player 2 might do, left or right, down is always the best strategy. And that is why we call the strategy down for player 1 a dominant strategy. Then let's move to player 2. If player 2 thinks that player 1 plays up, then what shall player 2 play, left or right? Left has a payoff of 2, right a payoff of 1. So left is better than right, and we underscore again the 2. Last question would be, what is player 2's best strategy? If player 2 thinks player 1 plays down, then shall player 2 play left and get a payoff of 1, or play right and get only 0. Of course the 1 is better, which is why we underscore the 1. So now player 2 has also a dominant strategy, which is to play left. Because player 2 plays left, no matter what player 2 thinks player 1 might do, up or down. So we have 2 dominant strategies. So now let's turn next to the concept of the Nash equilibrium. So when we played the game, and I'll just do it again, so let's play the game again quickly for player 1. So we said, if player 1 thinks player 2 plays left, what's my best strategy? Play up or down, and we underscored the 3. Then we said, what is player 1's best strategy if player 2 plays right? And if player 1 played up, gets 0, player 1 plays down, gets 1. That's why we underscored the 1. So no matter what player 1 thinks player 2 might do, down is always better. That's why we have a dominant strategy here. Then we move to player 2. What is player 2's best strategy? If player 2 thinks player 1 plays up, shall player 2 play left and get 2? That's better than 1. Of course, then player 2 will play left. If player 2 thinks player 1 plays down, shall player 2 play left and get 1, or play right and get 0? And of course, 1 is better. So now you can see that the combination of down for player 1 and left for player 2 is somewhat unique in the sense that as we played the game, we end up underscoring both payoffs. And whenever that happens, that is what we call a Nash equilibrium. And because that is a Nash equilibrium, I highlighted it in that light yellow color. But what does a Nash equilibrium mean? A Nash equilibrium is a situation in which no player has an incentive to move away unilaterally. So player 1 would have no incentive to say, you know what, I let player 2 play left and I move unilaterally to up. Because in this case, player 1 would lose -2. And player 1 wouldn't do that. Likewise, player 2 would have no incentive to say, I let player 1 play down and I move unilaterally to right. Because in that case, player 2 would drop from a payoff of 1 to 0, which is a loss of -1. So a Nash equilibrium in words is a situation in which no player has an incentive to move unilaterally. Okay, so another important term is the term of a social optimum. A social optimum is simply the aggregate payoff associated. The social optimum is the aggregate payoff that is the highest among all possible strategy combinations. So we simply sum up the payoffs. So for the combination up, player 1, left, player 2, we get an aggregate payoff of 3. For up, player 1 and right, player 2, we get only 1. For our Nash equilibrium, which is player 1 plays down and player 2 plays left, we get 4. And for the combination of down for player 1 and right for player 2, we also get only 1. So in this case, the Nash equilibrium consisting of down for player 1 and left for player 2 is not only the Nash equilibrium, but it is also the social optimum because it provides the highest aggregate payoff. And the social optimum does not need to make sure that all the players get the highest possible outcome, because obviously player 2 would prefer that player 1 played up so that player 2 can play left and then get 2. That would be the best for player 2. So that is irrelevant for the social optimum. So in economics, we are typically not concerned with maximizing a particular player's maximum profit, but the maximum profit for the society as a whole. And that is given by the combination of player 1 plays down and player 2 plays left. So our Nash equilibrium that we just derived is the social optimum. And whenever we have a situation like this, that's not a big deal. It's nothing really interesting in it, because the game ends up with a situation which cannot be any better for the society as a whole. But that will change when we look at a prisoner's dilemma. So a prisoner's dilemma is a situation where the Nash equilibrium is not the social optimum. So let's say the police captured Bonnie and Clyde, and let's say the police suspect that they robbed the bank, but they couldn't find the money, but the bank was robbed. But maybe they could find in their car a gun. And because they had the gun, they could already be held in custody and possibly sent to jail. But the police now suspects that Bonnie and Clyde may also have robbed the bank. And so now what the police does, the police essentially plays a game or designs a game that forces Bonnie and Clyde not to be able to cooperate. So Bonnie and Clyde, after they are being apprehended, they are immediately separated from each other. And now the police or the judge might tell them, okay, so here's the deal. If one of you confesses to also having robbed the bank while the other denies, the one that cooperates with the law enforcement or the police goes to jail only for 1 year. But those who deny, if somebody denies while the other one confesses, the denier, the non-cooperative player, goes to jail for 8 years. And if both confess, both go to jail for 5 years. And if both deny, both go to jail for 2 years simply because they already can be sent to jail, maybe for the illegal possession of a firearm or so. Okay, so the players know these are the rules of the game. So Bonnie knows that if she confesses and Clyde confesses, they go both to jail for 5 years. So obviously in this case, a lower number is better. But Bonnie also knows that if she denies to having robbed the bank, but Clyde confesses, then well, she would go to jail for 8 years and Clyde would only go to jail for 1 year. Likewise, if Bonnie confesses while Clyde denies, Bonnie goes to jail for 1 year and Clyde would go to jail for 8 years. So the best situation would be for them to both deny that they robbed the bank, and in this case they still have to go to jail for 2 years. But deny would be the social optimum for Bonnie and Clyde. But now what happens? So let's play the game. So if Bonnie thinks that Clyde confesses, what is Bonnie's best strategy? Shall she confess and go to jail for 5 years, or deny and go to jail for 8 years? Of course, the best strategy is to confess, because 5 years in jail is still better than 8 years in jail. But if Bonnie thinks that Clyde will deny that they robbed the bank, then shall Bonnie confess and go to jail for 1 year, or deny that they robbed the bank and go to jail for 2 years? And of course, going to jail for only 1 year is better than going to jail for 2 years. So Bonnie has a dominant strategy, which is to confess. And of course, because the game is symmetric, the situation is very similar for Clyde. So if Clyde thinks that Bonnie confesses, then shall Clyde confess and go to jail for 5 years? Or shall Clyde deny and go to jail for 8 years? Of course, confess is also better. And the last question would be, if Clyde thinks that Bonnie denies having robbed the bank, shall Clyde confess, go to jail for 1 year, or deny and go to jail for 2 years? And of course, 1 year is again better. So we can see, if we play that game, the equilibrium is that both will confess. That is their best strategy, but the Nash equilibrium is not the social optimum. The best situation for both would be to deny that's the social optimum, but that's not what the game leads to. But anyhow, so let's just stop here, and let's quickly summarize. So at this point, we already know what is needed to play a game. So we need to know the players, their strategies, their payoffs, and we already introduced some important concepts such as a dominant strategy, a Nash equilibrium, and a social optimum, and last but not least, what a prisoner's dilemma is. So let's stop here, and beginning with the next video, let's talk about some more games, specifically coordination and anti-coordination games.